Hi and welcome to another Motec webinar. My name's Pete Swinney and today's subject is M1 Fuel Tuning Basics. I'm coming to you from the Motec engine dyno cell, so things might be a little bit echoey and noisy at times, but we'll do our best. So, we're here to learn about how to tune an M1. The fuel method of calculating the fuel or tuning the fuel is very different from previous gold box ECUs. The fuel table is actually now the efficiency table, so it's a VE based tuning method, volumetric efficiency tuning method. Alright, so the shape will be similar to an M800 fuel table, but what the shape will actually represent is the engine's exact ability to flow air at any given engine speed or load, or manifold pressure in the case of the efficiency table. The shape is not affected by richer or leaner mixtures. It's not affected by fuel pressure curves. The only thing that will affect this shape is the engine's ability to breathe air, as was said. So the M1 calculates the air mass through the engine using pre-entered parameters. So for an example, one of the parameters that we would enter is the cubic capacity of the engine. So in an example, we might have an engine on the dyno that's 4 litres. So what that's the M1's calculating is if it sees a number in the efficiency table of 100, meaning 100%, what that means is that for every 2 engine revolutions, which is of course 1 cycle, the M1's expecting to see 4 litres of air pass through the engine. That's of course if it sees 100 in the efficiency table. So it calculates that airflow very accurately. It then is looking at the air-fuel ratio request, or the fuel mixture aim, which is entered into in the fuel mixture aim table. So if it's calculating a certain amount of air mass and it's looking for a certain fuel mixture aim, it then calculates that it wants a certain volume of fuel, and that's calculated in microliters. It then looks up the injector linearization tables and calculates exactly how long the injector needs to be open for any given fuel pressure or any given battery voltage. It then delivers that fuel and you get the fuel mixture aim that you're after. It actually uses the fuel mixture aim table constantly as part of the calculation. It's always looking at what you as the tuner want to achieve for a resultant air-fuel ratio at the exhaust. Alright, so it's really important to understand that for this system to work well, that you must enter accurate calibrations for everything. Now obviously sensor information must be accurate, but injector calibrations, fuel pressures, things like this, you must enter that information into the program in order for it to calculate the correct amount of fuel required. Alright, so that's a key thing about getting an M1 to work well, is to have accurate setup on those parameters. Alright, so just a little bit more on the efficiency map. So the process would be, you would enter your mixture aim, or your lambda, and your lambda table. That's what we'd call it in the M800, for example. In the M1 it's called the fuel mixture aim, and this is actually just the main table where you enter what you're after as a air-fuel ratio for the engine. There are actually lots of other tables that contain fuel mixture aim values, and in a different webinar that you can view later, there will be an explanation of how that all works, how the M1 chooses in fact the richest of any of the relevant tables to come up with a final fuel mixture aim for the calculation. Alright, so we also put in information about the type of fuel being used. So in the case of ordinary pump gas, we're entering a density of around 720 kilograms per meter squared, or cubic, and the stoichiometric ratio for that would be 14.7. If you're going to change to E85, for example, you're going to change your stoichiometric ratio and density to different numbers. We then want to enter accurate injector linearization table, and as I said there earlier, this is really critical so that the M1 knows for any calculated volume that it wants to add to the engine, needs to know exactly how much to open the injector by. This is especially critical down at the lower end of the injector operation, sort of under 3 to 4 milliseconds, where the most injectors are non-linear. So a simple 2D calibration just won't do if you want accurate air-fuel ratios to be calculated in everyday running. Right, we need to enter the cylinder volume, so our example was 4 litres. The number of cylinders, and again in the example, was going to be 6. And the fuel pressure. Also we need to know, is the fuel pressure referenced to manifold pressure? Has it got a boost hose on the fuel pressure regulator? Or is it maybe a fuel pressure reg and pump assembly that's sitting inside a tank? We enter those numbers. If you have a fuel pressure sensor, it's constantly using that fuel pressure sensor for its information. If you don't have a fuel pressure sensor, then it's looking at that default fuel pressure value that you're going to enter. So it's really important to enter all the accurate information into the defaults on all the sensors. Alright, so if you went through that process, and there is a separate webinar on the entire setup of an engine covered by Mark, and you can look at that. But if you enter that basic information, enter 100 into the engine efficiency map, the engine would actually run straight away. As I said earlier, a number of around 60 is a good approximation of what it would be for an engine to idle at, and numbers of around that 100, 110 are going to be around the peak torque numbers. If you have inaccurate injector calibrations, inaccurate fuel pressures entered, this will of course affect the actual outcome of the efficiency numbers. But if everything's entered correctly, then you should expect normal volumetric efficiency numbers that you'd be used to understanding. Alright, so the engine efficiency axis, it's always manifold pressure, and it's useful to understand why that is at the beginning. So what the M1's doing is it's calculating, it's using that efficiency table to calculate airflow through the engine. So as an example, if it's a 4-litre engine and the inlet manifold pressure is 50 kPa, it's expecting to get half an atmosphere of air through the engine at a efficiency number of 100%. So conversely or similarly, at 100 kPa or 1 atmosphere, 101 kPa, and as an example at an efficiency number of 100%, the M1's assuming then that this 4-litre engine is passing 4 litres of air through it per cycle. It then looks at the air-fuel ratio or fuel mixture aim table, and then looks at what the fuel is entered, what type of fuel it is, what the stoichiometric ratio is, and then calculates a volume amount of fuel to be delivered. Again, then it looks at the linearization tables and says, I want, let's say, 60 microlitres of fuel to go at this particular pulse width, and then opens the injectors for the correct amount of time to deliver that. So for this system to work, the M1 requires that the efficiency table have manifold pressure on its vertical axis. It's calculating airflow through the engine per kPa of air available to flow through it. Now, I can hear some of you asking, but I want to map it on throttle position. So what we give you, as you can see on the screen, is there are 3 options to determine how inlet manifold pressure is actually derived. So inlet manifold pressure itself can be derived from the inlet manifold pressure sensor. So that would be option 3. So if you entered 3, basically this would be exactly the same as tuning your M800, where it is simply an inlet manifold pressure sensor giving you the vertical axis of the efficiency table. Option 1, as you can see there, uses the map sensor reading, but then as a fallback, if the map sensor fails for whatever reason, then it actually falls back to an inlet manifold pressure estimate table. So that's a heap better than the M800 for instance, because it used to fall back to a single default value. Now, if you're really adamant that you want to tune this engine on throttle based, and that might be certainly a requirement for something that's multi-throttle body, or at least a large duration camshaft with a big single throttle body, you can use the estimate table to give you what's effectively a throttle based vertical axis on your efficiency table. So as you can see down here, there's a screenshot of our inlet manifold pressure estimate table. And this is something that you can quite quickly tune. You can guess it if you like, but what it means is that the efficiency table numbers won't work out right. So on the vertical axis of the inlet manifold pressure estimate table, you have throttle position, and then on the horizontal axis, of course, you have engine speed. So by going to each of these sites and entering what the inlet manifold pressure would be for any given throttle position and engine speed, you can effectively model what the inlet manifold pressure would be. Alright, a nice little feature of this table is that you can actually use the quick key, the Q key, to not quick lambda but quick enter the live inlet manifold pressure at the time. Obviously, if you have an engine without an inlet manifold pressure sensor, you're going to have to estimate this yourself. A nice way of doing it is to, even if it's only temporarily, connect an inlet manifold pressure sensor either across your multi-throttle bodies or into your plenum and use it to fill out this table or calibrate this table accurately. You don't have to use that sensor ongoing, but it gives us a real-world estimate of what is the available atmospheric pressure or inlet manifold pressure, what's the available pressure at the valve at that time. Later, when we tune the efficiency map, the engine will be able to make a reasonably close assumption of what the airflow through the engine is at the time. You'll still get the same, even if it miscalculates that, the result will still be the same. You'll be able to tune the efficiency map to make the engine richer or leaner. It just affects some things downstream that we can talk about later. Alright, a third axis on our engine efficiency table is ambient pressure. So this is for engines or vehicles that are doing hill climbs particularly. So on the engine efficiency table, and by pressing A, you can enable this axis just the same as an M800. And you get 6 load sites or ambient pressure sites to configure, and then the process of doing that is to physically set each site up. It automatically copies the same efficiency map into each position, and then go to each of those altitudes or ambient pressures and do your efficiency mapping. It then directly interpolates between each of those ambient pressures as the vehicle, which may be a Pikes Peak hill climb car, transverses from the bottom to the top. Alright, so just something that we've added to get that mapping as accurate as we can for those particular types of vehicles. Alright, so we've talked a lot about the mixture aim table and how it plays a part in this. And it's really important to keep hammering home to dedicated M800 tuners that the M1 uses this mixture aim table, which was the lambda table, as part of its calculation. So if you rock up to an M1 and maybe just jump online to it and change the mixture aim table, then what will happen is that will immediately change how the engine will run next time it's sent out. So the M1 is constantly looking and using the entered parameters in the mixture aim table along with the efficiency table. Alright, so changes to either table will affect the pulse width. The quick key or the Q key still works on the engine efficiency table just the way you would expect. It's the same as the M800. Alright, and it's looking up the current fuel mixture aim channel, which actually may not be the main fuel mixture table. What it's actually doing is looking for the richest of any of the aim fuel mixture aim tables. There could be a fuel mixture aim table for exhaust temperature that's sitting at 0.80 and the main table is sitting at 0.90. The system will use the richest of those fuel mixture aims to do the quick lambda function on the efficiency table. So once that efficiency map is tuned, that should be then left alone. There's no reason to change or tweak or change for any reason the the efficiency table after it's been set up properly. This is all provided, of course, that you've done and entered accurate calibrations for your injectors and the engine size and things like that. later and in future webinars we'll be able to show you the real difference that happens when you get all this right at the beginning. So what it means is that you can change your engine to be richer or leaner, not by changing the efficiency table, but just simply by changing the fuel mixture aim. Alright, just a note here that if you are using closed loop fueling, which you can obviously do, pressing Q when in this mode automatically trims or zeros the trim that's active at the time. So if you choose, you can turn the closed loop fuel on and you can be running the engine, and if you happen to be at 13% trimming rich, if you're at a particular load site and held steady at that, you can press the Q key and it will zero out the trim and apply the appropriate change to the efficiency table. Alright, now one last thing. There's two main modes that the efficiency table is calculated via, and we've talked so far about manifold pressure, and manifold pressure being the main sensor parameter, or not sensor, in fact it's a derived channel. So manifold pressure is what the efficiency table by default uses to calculate the airflow through the engine. Now there's actually a setup, an initial setup, page 1 I believe, that gives you the choice of actually not using manifold pressure but using ambient pressure as the method of measuring efficiency. So instead of efficiency per kPa, it becomes efficiency per atmospheric pressure. The simplest way to kind of explain that is if you think about how the M800 used to do your fuel map. When you had inlet manifold pressure as a 2D background compensation, maps used to sit flat, relatively like at the top of a large hill, and the number change from idle to full load really was only a representation of a richer mixture. In an M1, if you were to do a multi-throttle body engine, and the same with an M800, you don't really have an accurate reference to inlet manifold pressure. What that means is if you did try to do multi-throttle body engine tuning in the M1 with manifold pressure as the main calculator for the engine efficiency table, the resolution is all out of whack and the table shape just looks terrible. So you have an option to change how the efficiency table is calculated, and you can do that by changing to ambient pressure. Really the only time that you'd want to do that is when you're tuning multi-throttle body engines. Once you do that, the shape that you will see is not necessarily following normal efficiency numbers, but one where you have quite a small number at low throttle positions and quite a large number at high throttle positions, and it very much follows the similar shape that an M800 would show when you have no inlet manifold pressure compensation. Alright, that's it for today. We're going to do another webinar very soon, and hope to have you along to watch that. There's going to be many subjects coming up, and we'll cover as many as we can on the new M1. Thanks for listening in, and we'll catch you next time.